Hi, this is Sudeep Manchanda from Quite Easily Done. This video is a part of the series Know Your Component, and today we would be talking about transistors. This video would cover what is a transistor, the working of a transistor as an amplifier and as a switch. Before we move on to understanding what a transistor is, I would recommend, if you guys are not aware about the working of a diode, please refer to the video titled Diode under the Know Your Component section. This would help us get the very basic concepts that would be used in understanding the working of a transistor. So what is a transistor? A transistor is a semiconductor device which has got three terminals, namely the emitter, base and collector, and is extensively used in our electronic circuits. In the older days, we used to have vacuum tubes, which used to be huge and very heavy in power consuming, and also very slow in responding to our requests. Transistors have replaced them, have become very small. Any small component that we take, let's say for example, if we take a mobile phone, it has 1 million of transistors in that one big IC that we see. So transistor, its names comes from a combination of two words, which is transistor and resistor. Transfer of resistors is, in short, is transistor. We'll come to that when we understand the working of a transistor as an amplifier. So to simplify things, we would say a transistor is two diodes placed next to each other, and the way we place it, we would be coming up with two types of transistors, which is an NPN or a PNP. Now what we are talking of is a bijunction transistor, a BJT. So let's first understand what that means. So a transistor can either be a bijunction transistor, a BJT, or can be an FET, which is a field effect transistor. An FET, one of the common type of FET that you might have heard of is MOSFET, which is MOSFET. This video would cover only the BJT, and the rest of the type, the MOSFET, would be covered in another video. A BJT is, as I said, bijunction transistor, which means it has two junctions. A transistor can be understood as a bijunction transistor can be understood as being two diodes creating two junctions. So if we look at a representative diagram of it, we have is an n-type semiconductor, p-type and n-type, which basically creates a positive, like a diode like this and a diode like this, if we understand it in terms of how a diode would be there. So if you see, we have two junctions. I'll change the color. With this is a junction J1 and the junction J2. This is the reason why we are calling it a bijunction transistor. So one of these sections, we would be calling it as being the emitter, which will represent as E. The center one would always be a base, and finally the last section would be the collector. So collector is the one which is largest in size, base is ideally very thin, and an emitter is somewhere in between base and collector in terms of size. So what we have drawn over here is a representation of an NPN transistor, which means there is a p-type semiconductor sandwiched in between two n-type semiconductor regions. Similarly, we can also have is a PNP transistor, which is where the base is n-type, and next to each other, on either side of the base, we would have is a p-type semiconductor. One of them would be called the emitter, the other one would be called the collector. So the only difference is, in case of an NPN transistor, the emitter, which as the name signifies, would be emitting the majority charge carriers. In an NPN transistor, the majority charge carriers in the emitter would be electrons, And in case of a PNP transistor, the emitter would have the majority charge carriers as holes. If you understand the working of either of them, the other one would imply automatically to us, because in one the only difference is which is the majority charge carrier to us. So we have understood what an NPN and a PNP transistors are. So to be able to understand the workings of it, we will have to understand the two major modes in which a transistor is used. So a transistor is used as an amplifier or is used as a switch. So we see that a physical switch would help us switch on and off a device, which could be a light or a fan. A transistor can be used to digitally switch on or off a device. So that is how it would work as a switch, and we will first look into the working of a transistor as an amplifier. So let's go down, and we are trying to understand this while taking the example of an NPN transistor. So in an NPN transistor, we said, I'll make a bigger diagram. A small section would be the emitter. A very small section in between would be the base, and a big region would be the collector. The mode in which a transistor would work on would be decided on how do we connect it in a circuit. So a transistor can work as an amplifier in two modes. One is called a forward active mode, and the other is called a reverse active mode. We usually use the forward active mode for amplification purposes. We don't use the reverse active mode, and we will understand that reason also. So in order to have the transistor in a forward active mode, we would have to have the base emitter junction into forward bias and the base collector region into a reverse bias. So when we say a base emitter region, we are trying to look only at these two sections and consider them as a diode. So if this was an NPN transistor, in order to have the base emitter junction as forward bias, what we would have to do is we'll have to connect the emitter to the negative side of the terminal and the base to the positive side of the terminal. And we also said that the base collector would be into reverse bias, which here would become the other section that we are looking at now, basically saying us that when we are looking at the base and the collector region, we would have to connect the base to the negative because it's a p-type, and positive of the battery to the collector. So this is basically what we call as a configuration where it is a forward active. In order to understand what happens, we will look at the diagram on our right top over here. When we come up and when we do the connection, as we said, making the base and the emitter as forward bias, the emitter, which has the majority charge carrier as the electrons, these electrons would be able to cross over the junction into the p-type base, and we would be able to see a flow of current. This is what we have understood when we were looking at the working of the diodes, where in a forward bias the junction becomes very small and offers very low resistance to the flow of electrons. And so we would see the electrons moving in from the n-side emitter to the p-type semiconductor, which is the base, and also we would see is a flow of holes from the p-type base to the n-type emitter. This would cause a current flow. Now what happens is, we said that the base is very thin as compared to the emitter, so a lot of electrons would move in from the emitter to the base, and only a fraction of them would actually be able to get recombined over here with the holes in the base. So from the emitter there would be a lot of electrons that would move into the base, but not, because this region of the emitter is very high, the number of electrons that move in from here in proportion to the size of the base is very high. Let's say for a given size there are 10 free moving electrons over here, and for the size over here in the base there's just one hole that is available. So out of these 10 electrons that have crossed over the junction and come into the base section, only one of these electrons would be able to combine with the hole. Basically this electron would get lost in the base region. The rest of the 9 electrons, because of the velocity, would actually carry on to the collector region, and that is why the name comes. Emitter is the one which is emitting the electrons, which is the majority charge carriers in an NPN transistor, and finally collector is the one which is collecting it. So in depending on what is the specifications of the transistor, we would say alpha is what has crossed over to the collector. Alpha is the percentage of the electrons that will cross over to the collector, is usually around 92 to 95% approximately. So that is the number of electrons that would actually cross over to the collector region. 1 minus alpha is the amount of electrons which would be recombining into the base region, which is 8%, 5 to 8% only. So it's a very small percentage as compared to the entire number of electrons that the emitter is emitting. Now the collector region is the largest in size, because the collector would be collecting all the electrons coming in from the emitter, the 90 or 95% of the electrons coming in from the emitter, plus the minority charge carrier electrons in the base region also. Those would ultimately come up into the collector region, and because of how we have connected the transistor into the circuit, the additional electrons that we would see in the collector region would ultimately get attracted towards the positive of the terminal that we have over here. So we talked of the flow of current being the opposite of the flow of electrons, so we would see an inward flow of current IC. IB is the flow of current in the base, because there would be some electrons that would move out over here, which basically this flow of current is happening because of recombinations of electrons and holes in the base region. And finally there is an IE current, which is the flow of current from the emitter, which has happened because of the electrons crossing over the junction into the base region, and the holes coming in from the base region to the emitter region. So now if we apply the Kirchhoff's law over here, we can see that we have two inflowing currents and one outflowing. So Kirchhoff's law says that the inflow and the outflow of current should match each other. So IE, the emitter current, which is the outflowing current, would equate to IB, the inflowing current, plus IC, which is again the inflowing current. So this is one thing that we know for sure. So that is the transistors working in a forward active region. But now we have to understand how is that this transistor actually in a forward active configuration acting as an amplifier. So if you look at, interestingly, our emitter and base junction, which was on the left, is actually, so we have the emitter, we have the base, and then we have the collector. The emitter base junction, what we had done was, this was into the forward bias, so it offered a resistance which was nearly equal to 0, very low resistance. Then we had was the base collector region, which was reverse bias, thereby giving in a resistance of almost close to infinity. That is what we had talked of when we were understanding diodes. So we say that the emitter base is our input side, whereas the base collector is our output of the transistor. So we know by Ohm's law that V is equal to IR, and which is applicable on both the sides, and I, the current, is nearly the same at emitter and collector, which is saying it's around 95% of the electrons from the emitter goes into collector. So we're saying it's nearly the same, okay, for simplicity purposes. Now the voltage, input voltage, which is VI, and is the same current I into a very low resistance, whereas the V out is the same current into a high resistance. So obviously we know for a given value of V input, the V out is going to be very high because of the higher resistance offered at the base collector region. So what we have been able to do is we have been able to get a V output which is greater than V input, which is what we're saying is the amplification. Now depending on how do we connect the transistor into the circuit, we would either be able to achieve a voltage amplification, or we would be able to achieve a current amplification. Also, what we have to observe is the fact that we have been able to transfer the current from one region of resistance to another. So we are calling the device as transfer resistor, which is trans and ter from the resistor, which makes us transistor. So combining the two words, we actually get a transistor. That is why the device is called transistor. So that is the transistor in an forward active mode. The reverse active mode is similar. It's just that the collector, we try and bias it the other way around by making the base emitter junction as, let me change the color, as reverse bias, and the base collector region as the forward bias, which practically means we are using the collector as the emitter and the emitter as the collector. Now the working would happen similarly because we said it's the P region sandwiched between two N regions, but the efficiency of a reverse bias would be very low because the number of electrons that the collector would emit would be very high, and what the emitter would be able to collect is very low out of it. So we would have further loss of electrons, thereby we would be losing on amplification. So it does not make sense to be using a transistor in a reverse active mode, and so for amplification purpose we would be using it into forward active. Just for a reference point of view, we would be talking about it in detail during our series video called amplification, but we can use a transistor into two modes, which is a common base or a common emitter mode for amplification, and we would be talking about these in details when we would be talking about amplifiers in detail. Okay, so coming on to the next part of the transistor, which is to use it as a switch. Now to use it as a switch, we can use the transistor in one of the two modes. One of them is a saturation mode, and the other is called a cutoff. In case of a cutoff, we put both the junctions into a reverse bias, and in case of a saturation mode, we put both of them into a forward bias. So in case of a forward bias, the currents would flow, and in saturation mode, the transistor would act like an on switch. In case of a cutoff, it would act as an off switch. Now how do we achieve this? We have the circuit on the right over here, and this is the circuit which is same for both saturation and cutoff regions. We have an input V in, which is applied to the base, and then we have is the collector, which is the one which has the arrow is the emitter. The other one is this is an emitter because it has the arrow in it. The other one is a collector, which is connected to the positive of the terminal, and the emitter is connected to the ground. What happens is, let's say when we put in a 0 input to the base, so the base emitter voltage is, sorry, the base emitter voltage is 0 because this is 0 and this is 0, both of them are 0. So this is not a forward biased situation, right? So no current would flow from the base to the emitter, this is 0. And because the base is 0, this is an NPN transistor, sorry. So this is P, this is N, and this is P. If we have 0 on the negative side and some positive value on the positive side, sorry. So this is an NPN transistor. So if we have 0 on the positive side and some positive value on the negative, the base collector region is reverse bias. So base collector is reverse. Because the two diodes, which is the base collector diode and the base emitter diode, both of them are reverse biased, there would be no flow of current that would happen. And so this is acting equivalent to an open switch. That's what we said is the cutoff region. Now let's change. Now let's apply some voltage Vin to the base. So what would happen now is we would apply because there would be some voltage at the base and the emitter is on ground, we would have the base emitter junction as forward bias. We would ensure the configuration is such that when we apply some voltage Vin, we would ensure that the base collector is also forward biased. Now because we're saying both of them are forward biased, the flow of current would happen with almost nil resistance. So the equivalent circuit would become is a closed switch, basically making the switch on, the connection on, sorry. So if we apply, if our base is, I'm saying 1, which is some voltage is applied, this switch is on, and we would, in this case, the bulb would glow. If the base voltage is 0, the circuit is off and the bulb is off. So we have been able to use the transistor as a switch by just applying a minor voltage at the base of the transistor. Now this we would be using it a lot with the relays to be controlling our electronic circuits. So any transistor has a given specification of the current that it can take. What would happen in a lot of cases, this is just a bonus fact, is the amount of current that can flow through a transistor is limited. But if you're connecting, let's say, a motor between the collector and the emitter, or for that matter something which draws a lot of current, that current drawn by the device can become more than the specification of the transistor. In order to be safe, what we do is we give the input to the base, which is a logical low or logic high if we talk in terms of digital. We connect this to a relay. A relay is basically a device which, if current flows through it, would toggle a metallic thing towards one of. So let's say this is on, this is in an off stage, it connects, and let's say this is a motor. And I connect it this way. So this is a metallic strip over here which gets attracted by the magnet over here. So when I've given an input equal to 1, which is yes, current would flow through the metallic coils, would attract the metal, would connect it to one terminal over here. This circuit is open for the motor, so there has to be a power supply also. So the circuit is open for the motor, it does not work. Actually, this should happen in the case of 0. So In case of 0, the magnet is on, it's pulling it. If I toggle the input to 1, the strip would get connected to the other device, and the circuit would get completed and the motor would switch on. That is how you would actually use the transistor as a switch when trying to control external devices. This we would talk and see detail of this in a video called relay boards. So again, recapping it very quickly, we talked of what is a transistor, and we talked of what an NPN and a PNP transistors are. We also talked of how a transistor can work as an amplifier in an active mode, and we have also talked of a transistor acting as a switch in cutoff and saturation modes. Okay, that is it about the transistor that I wanted to share with you guys. Please let me know of your feedback. If you have any questions, please write it down in the comments section. Let me know if you want any other videos on any components that you don't understand. And see you next time. Thank you so much.